Good afternoon, I'm Jingzhu. Today I will present our work Themis. This is a joint work with my student Hongchen and our collaborators Ting and Guoliang. Distributed concurrency bugs often cause severe outages in production systems. For example, in 2025, a distributed concurrency bug led to an outage in Amazon's DynamoDB, resulting in significant financial loss. Let me first define distributed concurrency bugs. They involve two concurrent execution flows accessing the same object, with at least one triggered by internode communication. We focus on RPC-related cases, since RPC is a widely used communication mechanism. These shared accesses can lead to incorrect behaviors under certain interleavings. Let's look at a real example we detected and later confirmed by developers. It illustrates the execution model and how these bugs occur. First, we distinguish two types of clients. The test harness is an external client. RPC client and server functions are internal to the system for communication. The test harness invokes public interfaces, which are young child main and force queue task. Young child main calls RPC server function get task. Force queue task triggers another RPC and eventually calls onRegister. Importantly, get task and force queue task execute on the same shared server instance. The bug occurs when remove at line 582 executes between line 521 and 533. This leads to a double remove, making the task variable none and causing a non-pointer exception. Prior work relies on dynamic approaches, which depend on workloads and test suites, and therefore have limited coverage. To achieve both high coverage and high precision, we propose a new framework. We first use static risk detection for broad coverage, and then apply targeted testing to validate each detected risk to improve precision. Existing static risk detection typically starts from known entry points, either in the given test harness or within the system. From there, it enumerates concurrent execution flow pairs and analyzes them top-down to find potential risks. The key challenge here is that we are dealing with open systems. Distributed systems expose public interfaces that can be invoked by external clients. Without a test harness, existing top-down analysis does not work. Then our idea is to assume that any pair of public interfaces can run concurrently. Instead of enumerating execution flow pairs, we focus on RPC reachable variables and look for potential risks on them. In detail, we perform static risk detection without relying on a test harness. We assume that public interfaces can run concurrently. Starting from an RPC client-server pair, we extract variables along the call chain, find their access sites, and then look for another call chain that may rest on these variables. To validate detected risks, we need to build a test harness for each case. The challenge here is this requires both correct call sequence to establish system states and complex parameters to satisfy path constraints, which creates a huge search space. Our idea is to decouple these two tasks. Given the static analysis result, we leverage an LLM to generate a basic test case with diverse call sequence and cost parameters. Then we apply directed fuzzing to find parameter values that satisfy the path constraints. Finally, we manipulate access interleavings to expose the bugs. Since we use LLMs, a natural question is, how do we handle hallucinations? Hallucinations may cause the generated test to deviate from our target, and it's often hard to verify the generated test directly. Our solution adopts an LLM plus guidance plus checking paradigm. Static analysis guides generation, and fuzzing refines and verifies the results. Our framework Themis has 3 key modules: static RPC-driven risk detection, LLM-based holistic test generation, and staged parameter fuzzing and interleaving exploration. Now let's look at the first module. We start by localizing RPC-reachable variables and their access sites. Themis first identifies RPC client-server function pairs by matching their communication protocols, and further filters out pairs that use different configuration addresses. Themis then performs reachability analysis on both sides of RPC. On the server side, we traverse downward to find memory access sites. On the client side, we traverse upward to identify where parameters and return values are produced or consumed. For each access site, we extract the variables and label it as read or write. For parameters and receiver objects, we use points-to analysis to resolve the referenced variables. After extraction, we keep only variables that may be shared. On the server side, the server is long-lived and handles requests concurrently, so its instance fields are shared. We also track static fields and IO/NIO objects. On the client side, we keep all variables. We collect all access sites for each variable within its declaration scope. We use points-to analysis to keep accesses that refer to the same variable and label them as reads or writes. For IO/NIO objects, we further analyze file paths to detect aliasing. For example, we extract all the access sites of JVM map. Themis then applies analysis rules based on the extracted variables and their access sites to detect violations. Themis captures all the violations and atomicity violations. Let's say rule 1. Rule 1 detects 2 functions accesses to the same variable, and at least one access is a write. Rule 2 captures atomicity violations where one function accesses a variable twice, and another function's access happens in between, forming a 3-access interleaving pattern. The remaining rules extend this idea to concurrent executions of the same function and asynchronous execution within one function. Rules 1, 2, 3 apply to both RPC server and client sides. In contrast, rules 4 and 5 are client-specific. Back to the example, it matches rule 2. Get task accesses JVM map twice, and unregistered accesses it once, forming a read-write-read interleaving. This leads to an atomicity violation between the 2 functions. For each detected violation, we extract the corresponding public interfaces. For rules 1, 2, 3, we extract the interfaces invoking the 2 receive functions. For RPC call chains, we trace back to the client-side public interfaces. For rules 4 and 5, only one public interface is needed. For atomicity violations, we prune cases protected by synchronized methods or blocks. Customer synchronization is hard to analyze statically, so we leave those cases to the testing phase. To filter out the benign races, Themis checks whether the racy accesses lead to symptoms. Themis checks whether the incorrect state introduced by the race can propagate to explicit failure statements through control or data dependencies. We call these cases EA and EO. Themis also considers implicit symptoms, focusing on 2 common runtime exceptions, non-pointer exceptions and out-of-bounds exceptions. We define 5 error patterns. For 4 of them, the failure occurs directly at the racy access. Only the MR pattern requires further propagation analysis. This example matches the MR pattern because the remove operation may return none, and the return value is used without a non-check. Given the complete execution path of detected races, Themis uses an LLM to generate test harnesses. The goal is to construct a test that prepares system states through necessary call sequences. The execution should proceed without runtime errors. A violation may be reachable from multiple public interfaces. We prioritize the most promising ones first. For each violation, Themis follows a generation and repair workflow. We first generate an initial test from the static analysis results. If the test fails at runtime, we iteratively repair it using error messages and code context. If repair still fails, we restart generation. After several retries, we also incorporate existing test suites to reuse useful call sequence. For this example, Themis generates the call sequence, but the parameters still need adjustment. To expose concurrency bugs, Themis needs to satisfy 3 conditions: reaching the RPC statements, triggering the buggy interleaving, and finally manifesting the failure symptoms. We address these goals in 3 stages. In stage 1, we use directed fuzzing to refine parameters so that execution reaches the target access size. Stage 1 sets fuzzing targets at RPC call size, RPC server functions, RPC functions, and RPC access statements. In the example, LLM-generated parameters do not reach all targets, but fuzzing adjusts them so the targets are eventually reached. After reaching the RPC accesses, Stage 2 explores all relevant interleavings for each violation. Stage 2 uses a signal and wait mechanism. For order violations, we test both execution orders. For atomic violations, we test whether one access occurs before, after, or between the other 2 accesses. A violation is confirmed only if the symptom appears under the buggy interleaving, but not under the others. Back to the example, the non-pointer exception only occurs under the specific interleaving. Even if a race is triggered, the bug may still not manifest because the failure conditions are not satisfied. To address this, Stage 3 uses fuzzing again to trigger symptoms. Stage 3 adds symptom statements as additional fuzzing targets. It reuses the seeds and parameters from Stage 1, since the RPC accesses have already been reached, and the remaining goal is to trigger the symptoms. During fuzzing, we check whether RPC and RPC accesses are reached, as in Stage 1. If so, it further explores the interleavings and checks whether the symptom is triggered, as in Stage 2. For implicit errors, reaching the symptom statement is not enough. For example, here, a non-pointer exception occurs at S3 only when JI variable is actually none. So, Themis instruments checks that transform error triggering conditions into explicit control flow branches. We have implemented a prototype of Themis. We evaluate it on 8 popular cloud systems to measure its detection capabilities. We also construct a known bug set to evaluate whether Themis can detect them. We report both number of violations and number of bugs. A single bug may correspond to multiple violations, which can be fixed by the same patch. Themis detects 204 unique violations, including 198 new ones, which correspond to 58 bugs. 52 of them are new. The superscript in the table shows how many violations correspond to known bugs. We have already reported all new bugs, and 6 have been confirmed so far. 170 violations exhibit implicit symptoms. Most bugs rest on server instance variables. This highlights a common pitfall. Developers often overlook that multiple RPC clients concurrently invoke functions on the same server instance, leading to harmful bugs. Static analysis detects 239 unique violations. We successfully generated test cases for 228 of them. In the end, Themis exposes 204 true violations. To conclude, this paper presents Themis to detect distributed concurrency bugs with substantially improved detection coverage. Evaluated on 8 real-world systems, Themis detects 52 new bugs. That's all for my talk. Thank you for listening.